Here we go. We want to make sure that we're smart about this, and we want to make sure that we're doing the work. Because if you are not putting your brain through the paces, then you're not learning. You're all very good handwriters. You're all very good copiers. But this is sometimes why I intentionally walk out of the room. I walk away because I want you to turn to your partner and be like, hey, explain this to me. Or hey, I don't get it. Or hey, because you have to do it by yourself. You can't continue to depend on what it is that I do. And until you see me do it, you don't know what you don't know. I have to measure the minor arc formed by the hands of the analog clock. Let's talk about this clock as a circle that we recognize. I know that the distance around the clock is my circumference. I know that the center of the clock is my center. And I know that each of these hands represents radii. So I need to know what is the angle that is inside there before I can figure out the measure of that minor arc. Measure is not length. Think right now, the difference between measure and length is what? The measure of an arc is what? The length of the arc is what? What's the difference? Degrees versus, right? So do we know how big my clock is? Not yet. Maybe we do in number 2, but my clock could be this big. My clock could be this picture of it that I have on my watch. My clock could be the big one that's on my kitchen wall, right? The clock could be the big one that's on clock tower down on the other side of the toll road. I don't know how big my clock is, but I do know that these 360 degrees are divided up into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pieces. So if 360 degrees is divided evenly by 12, how much is each individual central angle? 30 degrees. And if I have 1, 2, 3, 4, 5 of them, what is this measure of this arc here? 150 degrees. So I have 360 degrees divided by my 12 sections of my clock, which means they're each 30 degrees. I've got 5 sections of that 30 degrees, giving me a total of 150 degrees for that central angle. So the measure of the angle equals 150 degrees, therefore the measure of the arc is also equal to 150 degrees. That's really diving deep down and making sure you understand why things are what they are by looking at the connections between the vocabulary and the math. Now I know how big my clock is. My clock has a radius of 8 inches. It's about that wide. So it looks like it is my clock. That looks like it could be a radius of about 8 inches. So, okay, the clock has a radius of 8 inches. How far around the outside of the clock does the big hand travel to meet the little hand? Now, we're going to make this problem simpler because we're going to say our little hand isn't moving. Because you know that as this big hand moves, this little hand does shift. But we're not going to talk about that. So that's a system of equations. It's a super cool calculus problem, but we're not going to go there today. When I talk about how much does it take to travel this distance to the 5, what I want to know is if I have 150 out of the 360 degrees, what is the length of that compared to the entire distance around the clock, which is going to be my circumference, which is 2 pi r. We keep doing things in 2 ways because maybe it's easier for you to see that distance is equal to this fraction of my whole distance around. So when you pull up in your calculator and you can say, all right, 150 divided by 360, that fraction is that decimal. Of is my multiplication, 16. That's going to give me math, frac, enter, 20 thirds. So we'll say that's 20 thirds pi. Or if they want us to give it to them rounded to the nearest hundredth, I can multiply that value by pi and say that that distance is about 20.94 inches. Sound okay? Thumbs up if you got it. Awesome. All right, problem 3. In circle B, the length of the arc is 3 pi inches, and the measure of the angle is 120. What is the radius? So that's the one we talked about where we start looking at things from a different view. Where we go from, and you need to decide, is this easier written as a proportion, or is easier written as an equation where I know something is the fraction of something else. So let's fill in our values, see where our missing value is, and make a choice on how we want to solve it. I know I have 120 out of the possible 360 degrees are out there. I know the length of my arc is 3 pi, and I'm comparing that to twice pi times my radius, which is what I'm looking for. So there's my unknown value in the denominator of that fraction. Cross products, multiply, divide to solve for r, not a problem. If I do it with an equation, my math looks like this. My length is 3 pi, and I know that's this fraction of my circumference, 2 pi times my radius. There's my unknown. And untangling that r is totally up to you. That's algebra that you learned last year, and you're like, no, I didn't. But now it's time for you to learn it. So however you want to untangle that, what should your first step automatically be that makes everything so much easier? What do you want to do?
Get rid of pi.
Let's cancel out the pi. So we're going to get rid of him. Naheen says, anytime I have the same value in the numerator and denominator of a fraction, that's equal to 1. Away it goes. That makes that a lot easier. If I do cross products, that gives me 2r times 120 is equal to 360 times 3. You can solve for that, r. That's not hard. If I have the same value being multiplied on both sides of an equation and no addition or subtraction signs, I can go ahead and divide by pi and have that be my first step. And then let's see how much simpler this equation becomes. 3 is equal to, I can go ahead and simplify this. The first thing I do is cross off my zeros. 12 over 36 sounds like 1/3 to me. 1/3 times twice my radius. I don't know which one you think sounds easier to get r out of. Here's my r here, here's my r here. Here I can multiply 360 by 3 and divide it by 240. Here, all I need to do is multiply by the reciprocal. Remember that reciprocal is the magic number that's going to cancel out what's in the numerator and denominator at the same time. So if I multiply by the reciprocal, I'm going to end up with 9/2. So I have the radius equal to 9 over 2. Let's see if I get that same answer over there. 360 times 3 is equal to that. And I'm going to go ahead and divide that by 240. And if I go math, frac, enter, 9/2. So it doesn't matter which way you do it. Raise your hand if you like the proportion. Raise your hand if you like the equation. So at the end of the day yesterday, last class, we ended up being asked to find the area of a sector that looks like this, a segment that looks like that. But part of that comes from being able to find the area of that triangle, because the area of the segment is the area of the sector minus the triangle. So Mr. Logan and I were looking at this problem yesterday, and I solved it one way. He solved it a different way, but we both got the same answers. So what I want you and your group mates to do is come up with, and there's actually 3 ways to solve this, maybe 4. So go ahead with your group mates. Figure out what the area of this triangle is given this information on your marks. Get set, go.
Alright, you guys
That actually means that this that's each doing. Okay, so that means that that's 120. So that means this is
and then the area formula. So radius is before plus
But this is 41.
what? This, yeah, this.
I blew it up to make it bigger so that I could fit more of my numbers in it. There is no shortage of paper in math class. If the drawing that you're working with is getting crowded and muddy and ugly, get a piece of paper and redraw it bigger. Because then if you can be neater and put your angle measurements in and your side lengths in, then you can maybe see a better picture of the relationship between the things. I cloned it and I drew it twice because I'm supposed to find the measurements of the area of the triangle in 2 different ways. Anytime that you want to find the area of a triangle, I know that my area formula is always 1/2 of the base times the height. That is knowledge that should be in the front of your brain. We just did a polygon unit where we talked about it, and Mr. Logan and I had a debate. Did we have you find areas of triangles back when we did Pythagoras? I want to say yes, we did. He said no, we didn't. But you know how to find areas of triangles because you're supposed to be able to do that in the 5th and the 6th and the 7th grade. Is area of triangles new to anybody sitting in this room? It's okay to say yes. Is it new to any of you? Okay. Because he and I debated about it yesterday. He's like, we haven't taught it. I'm like, yes, we have. And he's like, no, we haven't. And I'm like, okay, well, if we haven't taught it, they walked in the door knowing it. And he's like, maybe not. Like, did you walk in the door knowing it, or did I teach it to you? You walked in the door knowing it? All right. 1/2 base times height. Now, here's the tricky part about a triangle. What's the base? Right? Right? You can have a couple different bases. But you need to make sure that the altitude, and I know we talked about this with parallelograms, you need to make sure that what you're calling your base and your height, that height goes to that base. So in this triangle on the left, do you see here that this is my base and this is my height? Yes? On this triangle on the right, do you see that this is my base and this is my height? So when I rotate my triangle around, I can have 3 different bases. Now this triangle is isosceles because its sides are radii of the triangle or of the circle. So it's isosceles, so both of those sides are a measure of 4. Because that's half of the diameter. Can you even believe the geometry we've just covered in that one sentence? Half of the diameter is the radius. The radius is the side of the isosceles triangle. Lots of vocabulary. Are you with me? All right, now we're going to bring in some right triangle trig. Because I can draw an altitude as long as I draw a segment from a vertex to the opposite side using a right angle. So this is an altitude that I drew from a vertex to the opposite side using a right angle. Now it happens to be outside of the triangle because this is obtuse. And when I have an obtuse triangle, that altitude or that height is outside the triangle. That's okay, we saw that with parallelograms. I used to have a picture here of it. This is the height that I drew to this base. This height is not the same length as this height because the height to the base is not going to be the same, but that area of that red triangle will be the same no matter what. So when I go to do my calculations for this one over here, I know that my area is equal to 1/2 of my height times my base. Now I gotta figure out what my height is. If my green angle here is 60, then this angle here is a 120. My altitude split that angle evenly because my triangle is isosceles. Are you okay with that? So that means that each of these angles is 60. If these angles are 60 and I have right angles, I know these guys are 30. I now have a 30, 60, 90 right triangle. And if you want to draw that triangle off to the side with your x, 2x, and x root 3 story, absolutely go ahead, do it. Because I know that my hypotenuse is double my short leg. You know it too. There it is. See it? My hypotenuse is half of my short leg. My hypotenuse here, my hypotenuse is double my short leg. My hypotenuse here is 4, which means my short leg is 2, which means the height of my triangle is 2. Thumbs up if you know where I got that number from. The base of my triangle is these two long legs put together. If my hypotenuse is 4, my short leg is 2, and my long leg is 2 roots of 3. So this piece is 2 roots of 3, and this piece is 2 roots of 3. So if you have 2 kitty cats, and I have 2 kitty cats, together we have 4 kitty cats. If you have 2 calculators, and I have 2 calculators, together we have 4. If you have 2 roots of 3, and I have 2 roots of 3, together we have 4 roots of 3. So the base of that triangle is going to be 4 roots of 3. That's that side's calculations. Now what's going to happen is the same output. When I multiply them together, my 1/2 and my 2 cancel out, so I know my area is 4 roots of 3. I better get 4 roots of 3 over here or I screwed up. So let's go ahead and see what I get. I know my area is equal to 1/2 of my base times my height. So what is the base of this triangle? 4. So we'll go ahead and put my 4 in there. Now the height of my triangle, you can see here, I just dropped an altitude and used this 60-degree angle. So if my hypotenuse is 4, my short leg is 2, and my long leg is 2 roots of 3. So then I can go ahead and recognize 1/2 times 4 times 2 roots of 3. Now, is there a right or a wrong way? No, because the question came from find the area of this segment. And the area of the segment you get by subtracting the area of the sector minus the area of the triangle. If you can't find the area of the triangle, you can't find the area of the segment. Stare at those 2 pictures. Which one makes more sense to you, left or right? Think about it for a minute. Some kids have a really hard time seeing this triangle outside of an obtuse triangle, this height. Some kids have a real hard time splitting this in half and seeing this as the base if it's not sitting on the bottom. Thumbs up if you like the picture on the left. Thumbs up if you like the picture on the right. Okay, we're about half and half. 2 ways of doing that, both completely good. Neither one is going to give us full credit because we still haven't answered the question, what is the area of that segment? So we're going to have to subtract 4 roots of 3 from this segment area. Make sense? Here's some challenge ones for you. We want you to find the area of the shaded region and express your answers in terms of pi and rounded. So there's 2 for you talk to your group mates about a plan on how to solve on your market set top. Go.
Alright, let's go guys.
Alright, so let's talk about the first one. I love it when I overhear somebody go, oh, this is easy. We can do this. Which is what I heard. Let's talk about what's in blue first. 90 out of 360, that's 1/4, times pi r squared. So that's 1/4 of 25. So I've got 25/4 pi. Area of that blue sector, easy peasy, summer squeezy, right? Say yes. Yeah. Okay, it's a quarter of the circle. Find the area of the whole circle divided by 4. It's a quarter of the circle. Let's talk about this purple sector. This purple sector, I have 40 out of 360 degrees times pi r squared, which gives me this. I don't know if you watched me do it or not, but this common denominator calculator math, totally on the calculator. I know how to find a common denominator. I can do it if I wanted to, but if I have a resource that does that 5th, 6th, 7th, 8th grade math for me, I'm using it. So I typed in 25 divided by 4 plus 25 divided by 9. I hit enter, math bracket enter, and it gave me 325 out of 36 pi. Are we good with that? I found this separate area. I found this separate area. I added them together and I got this. What did I do in red? My work in blue is the blue sector, and my work in purple is the purple sector. Easy peasy. Added those two areas together, I got the right answer. In terms of pi, unrounded to the 100th. I'm in good shape. What did I do in red? What's going on with the red?
Sections together.
Yeah, Artemis like, look, you didn't have to do this work twice. Hey lady, pay attention. You could have been smarter. You didn't have to do the blue and then do the purple and then add them together. You did, and you got a good answer, and it's right, rock on. But if you're a thinker and you're like, wait, that area is these, if this 90-degree sector was adjacent next to that 40-degree one, could I add 90 and 40 and just do the calculation once using a 130-degree arc? So my answer to that is yes. You can be smarter about this if you want. You can do 130 out of 360 multiplied by 25 pi and do that once and avoid doing all these calculations. Your choice. And I need to show you that there's more than one way to solve a lot of this math. And just because what pops into your head isn't what I do, you might still be right. And this is the balance that Mr. Logan and I fight every day. How much of the shortcuts should we show you? How much broken down? This is it broken down into pieces. Now you see it. Next time you might do this instead. That's called learning. Yay! We came to school for a reason. I love it. All right, remember I said that there were 3 ways to solve that triangle, and you're like, I feel like you left us hanging because you showed us 2. Guess what? This special right triangle goes back to Pythagoras, which goes back to trigonometry. Now, that 30, 60, 90, 45, 45, 90 special triangles, we learned them first because they gave us a peekaboo into the relationships and the ratios that work for all right triangles, regardless if they're special or not. So I have a not so special triangle. In blue, I found the area of the sector. So my work in blue represents the area of this, and my work in green is going to be the area of this. And guess what I can do? I can turn any triangle into a right triangle. If I have a side length and if I have an angle, I can go ahead and do that. So when I look at this triangle, I can draw this altitude. And if I want to look at just this right triangle that has a radius or a hypotenuse of 2, and this angle, my theta, as 37.5, if I needed to figure out the height of that triangle, I could with trig. If I needed to figure out the base of that triangle, I could with trig. This is what it looks like. Are you ready? Let's go ahead and solve for my height first. Are you okay? I'm hesitant to give it an H because I don't want you to think it's an hypotenuse. So I'm going to go ahead and call it X. Are you okay with that? All right, let's talk about this angle. For theta, what relationship is X to theta? Adjacent. What relationship is this side to theta? Hypotenuse. Which of my ratios is the story between my side that's adjacent to the angle and the side that's hypotenuse to the angle? Cosine. So I'm going to say the cosine of a 37.5 degree angle is equal to the relationship of the adjacent, that's what I don't know, over the hypotenuse. So now what I want you and your partners to do is remind each other, I don't know how to solve that, can you help me solve that? And then I want you to write a second trig ratio to solve for this one, we'll call this one y. Okay with that? Ready, Marcus, say go. When I look at my trig ratio and I check my mode, now I'm ready to type this in. 2 times the cosine of this angle, and that is the unit scale factor of every single right triangle that has a 37.5 degree angle. This scale factor of the two sides. What is the relationship? It's whatever's inside this calculator that's stored. I could go to a chart and look at it, or I could just count on the calculator. And the calculator is going to tell me that's a pretty small side. 1.59. You okay with that rounding? Say yes?
Yes.
So I want my x value to be 1.59. If I put that back in the context of my triangle, does it make sense that my long leg is smaller than my hypotenuse?
Yes.
Yes. If you got a value bigger than your hypotenuse, you screwed up. Go figure it out. See what I'm saying? Now we have a choice for the next one. We can do Pythagoras. A squared plus b squared equals c squared because we have 2 of the 3 sides of a right triangle. If you're in the trig mode and you're already doing it, you can continue doing trig. If I wanted to solve for y, what trig ratio am I going to use for theta with y and 2? I'm going to say the sine of a 37.5 degree angle is going to be equal to that y value over my hypotenuse. I'm going to go ahead and put this over 1 and say 2 times the sine of that angle is going to be equal to, was I expecting this side to be smaller than my first?
Yeah.
Yeah, because it's opposite the smaller angle. It's opposite the 37 degree angle. So that means that my y has a value of 1.2 what? 1.22. So I'm good to go. So now I'm going to look at, here's my x and here's my y. Just sit down. Now I gotta be like, oh gosh, what am I gonna do with those numbers now? How am I gonna get that back into my triangle? So just walk the dog backwards and figure out what you just solved for. Your height of the triangle was 1.59. Your short leg was 1.22. Are we all okay with that? Say yes?
Yes.
I'm going back to finding the area of this triangle. I know the area of that triangle is 1/2 base times height. my area is equal to 1/2 of my base times my height. My height I have 1.59. What is my base? 2.44. Where did I get that from? It's double. Here's this 1.22. Here's this 1.22. I have to add them together to get 2.44. Good Lord. All right, let's do it. Clear the calculator out. And I have 1/2 times my base, 1.59, times my height is 1.59, 2.44 is my base. There I have the area of what? What is that the area of?
The triangle.
The triangle. Is that what the problem's asking me?
No.
For the love of God. What is it asking me? That area of that segment. So here I go back to my sector area. And what do I do, Maheen?
Subtract
You subtract it. Which one's bigger, the triangle or the sector?
the center.
The sector. So I know 5 divided by 6 times pi was the area of my sector. And I'm going to cheat. Because I'm going to subtract. Why would I do second ants? Oh, so that's not going to work. So guess what my calculator can do? If I do clear. Darn it, I lost it. Oh, I wanted to show you something new. Hold on a minute. Bear with me. 5 divided by 6 pi is that. Shoot. This number was above. Your calculator, you can arrow up and press enter and pick that. I wanted to show you that. Oh well, minus 1.94. That sector area is going to be 0.68. We're not going to. The reason why we're not going to write this one that's square feet. The reason why we're not going to write this one in terms of pi is because we ended up estimating with the trig ratios anyway, so we've lost that exact value. We're going to give you a delta math with some of these puzzles where you're going to have to be a thinker about finding the areas of the different pieces and either adding or subtracting to get them. Would you please for a moment process this warm-up? Talk to your group mates about what is sticky, what is tricky, what you need to work on. Marcus, say go.
Alright, okay, so
We're going to shift gears and talk about some pretty cool properties with circles and tangents, chords and arcs. I'm going to give you a warning. When I say these, you'll sit there and go, oh, that makes sense, and then they all get jumbled up. So take the time to take good notes and ask questions when you don't understand, because we want to make sure that you understand the vocabulary and how it's all related. We'll get to the back of your warm-up in a minute. So we talk about vocabulary that we want you to know. There's tangent lines, there's a point in tangency, and then we can talk about the word tangent in terms of both a noun and an adjective. So when we talk about a tangent line, this line here that intersects this circle is a tangent line. A tangent line is going to be a line that intersects anything once. So I can have a tangent line to a parabola. I can have a tangent line to a 3D figure. I can have a tangent line to anything. This blue line is my tangent line. That point that it touches is going to be the one exact point that those two graphs share. I've got a circle and I've got a line, and they just touch in that exactly one point. That is my point of tangency. Now, when I use the word tangent, you need to be smart and say, okay, is she describing a thing or a relationship? So when I say that this tangent line is tangent, I'm describing a relationship because I'm saying that this line that's tangent has a tangent relationship. It touches the circle in one place. All right. The first property that we're going to talk about is when we have a tangent line to a circle. And a couple things happen. If a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. So if I have circle Q, and this line P is tangent, that means it intersects it at exactly one spot, and those two lines are going to be perpendicular. So I'm going to have a perpendicular relationship between. So as that radius slides around the center of that circle, it's going to maintain a tangent relationship. So a lot of times I can show this by thinking about if I have my handy dandy wipe container and my super de-duper orange ruler. If I were to look at this circle here, any place that this ruler is touching is tangent. So it's touching it in exactly one point. No matter where I stop, if I were to draw a line from the center up to this, it would be perpendicular. So as I rotate my tangent line around my circle, you can see that at any point, if I drew a line from the center to that point of tangency, it's going to be tangent. It's going to be perpendicular to that tangent line. So no matter where this line hits the circle, the radius that connects that point of tangency is going to be perpendicular. All right, then we can read this backwards. So this is going to be the converse of that. In a plane, if a line is perpendicular to the radius of a circle at the end point of a circle, then the line is tangent. So here is what our output is, then the line is tangent. Here, my output was then it's perpendicular. So if you put those two together, you get a biconditional scenario. Are you okay with that? So this one's pretty cool because it says if you have two segments from some exterior point, S, and they are both tangent to a circle, intersecting at R and intersecting at T, then these two lines are going to be congruent. We can go ahead and think ahead proof-wise and like dig down into our geometry and see why we think that's true. Go ahead and draw on your notes a radius from the center to the point of tangency. What kind of triangle do you have? It's not obtuse. It's what? It's perpendicular. So what kind of angle and what kind of triangle do you have?
Right triangle.
You have a right triangle. So go ahead and draw an imaginary triangle side, creating two triangles. How do I know those triangles are congruent? I don't see a second angle. I see hypotenuse leg. I see this leg because the blue legs are both radii. I see the pink leg because it's reflexive property. And I see the right angle. So I see hypotenuse leg. Where do you see your other angle? My pink segment is the hypotenuse. Do you see it?
Just reflexive property.
So the greens you don't have yet. The greens are what the theorem is proving. My radii are congruent. My right angles are congruent. This pink segment is reflexive property congruent. I see hypotenuse leg. Because of CPCTC, now I have this. I don't have the green until I get the congruent triangles. All right. So for this rule, we're going to have a couple practice problems where we can end up coming up with all sorts of right triangles to play with. For circle C with a given radius of 6, so my radius here in circle C is 6. Find the value of x. What do I know because of that first theorem? It's going to be perpendicular. And what you should be asking is, wait, is this tangent? Yes, it is. So then that's perpendicular. So then I know that my side length of 12 squared plus x squared is going to be equal to 25 squared because of my Pythagorean theorem. A squared plus b squared is c squared. 25 is my c because it's the longest side. Opposite of my hypotenuse. So my x squared is going to be 625 minus 144. So 625 minus 144, 481. By x is equal to the square root of 481. When I think about 481, is that divisible by 9? No. So we'll go to y is equal to, and we'll do 481 divided by all the numbers in the whole wide world. We'll go to my table and go to my table set. Mine's messed up because of what we were doing in calculus, so give me a minute. Anything evenly go into 481? Oh, 13 and 37. Any chance of simplifying that radical? How do I know? 13's prime, and so is 37. There you go. That's my value of x. Line segment AB is tangent to circle C at B. That's what I needed to know. I love it. Line AD is tangent to circle C at D. Got it. If I want to find x, what do? Set up an equation because both of these tangents from an external point, I know that they are going to be congruent since they're both tangent from A to the circle. So both of those are going to have the same value. When I solve for x, subtract 24 from each side. That looks like 25 to me. Take the square root. X is going to be equal to 5. Can I say plus or minus in this scenario? Can 5 be can x be negative 5? Yeah, we'll square away the negative. That's a good answer. Two rules that you have to remember. When the tangent and the radii meet, it's perpendicular, and two tangents from an external point are going to be congruent. Go ahead, talk about your partners for this one. Go.
Alright, guys.
So we're looking at more Pythagoras coming at us, which I love. Anytime we get a chance to review our right triangles, bring it on. So when I look at that radius, I know it's gonna be perpendicular to that tangent line, making r plus 4 my hypotenuse. So my a squared plus b squared equals c squared. Now again, that's the geometry. What you're looking at here is the geometry. The rest is algebra. So when we look at r plus 4 and we need to know, wait a minute, 4 plus r times 4 plus r, remember, that is your FOIL, first, outer, inner, last. That's your double distributive property. So 4 times 4 is 16, 4 times r is 4r, r times 4 is 4r, and r times r is r squared. So I combine like terms to get 16 plus 8r plus r squared. And I have that uh-oh feeling in my tummy where I'm like, oh, I see a quadratic. I'm going to have to set it equal to 0 and, factor to solve. And then I look at the other side of the equation. I'm like, no, I'm good. Because if I have the same thing on both sides of the equation, they will cancel each other out. Subtract r squared from each side. Dodged a quadratic. And then it's just simple algebra to solve for r. Alright, here's some more properties of your chords and arcs. Ready? When I have a circle, or in congruent circles, congruent central angles have congruent arcs. So that means that if I have this as a measure of x, and I have this as a measure of x, that means that these two central angles are going to have the same arc measure that defines them. So the distance from A to B is going to be the same as the distance of C to D. That kind of just makes sense to me. When we have that converse, it goes back. Okay, so if you have congruent arcs, then you have congruent central angles. So when we talk about this measure and this measure, I'm talking about in both degrees and lengths. So that measure of the arc is going to be the same too. By congruence, they're going to have the same distance. They're going to have the same measure. So when we measure arcs, it's in both degrees and length. And the reason why we're talking about length is because we're told that our circles are congruent. So those arcs will have the same distance. Guess what else is true? If you have a congruent circle and you have congruent central angles, you're also going to have congruent chords. So this chord is going to have the same length as that chord. So the arcs and the segments, the chords, the angles, all going to be congruent. So theorem 9.4 is about the arcs. Theorem 9.5 is about the chords. So you want to make sure that you are aware of both of those. So if we look at this, we can go ahead and see, because I have two congruent arcs in two congruent circles, then I know the distance from P to Q is the same as the distance from A to B. And I know that this angle here is going to be the same as that angle there. And if we really want to go down the rabbit hole, we know that vertical angles means that this angle is also congruent. So this chord is also congruent, and so is this arc. It's all part of the same thing. Another seemingly silly rule in the same circle or in congruent circles. And this sentence here, it just guarantees that the circles are the same size with congruent radii. So we're just saying it's not a matter of all little circles compared to big circles. We're talking about circles of the same size. If I have two minor arcs are congruent, then that means their chords are congruent. That means their angles are congruent. So, and notice I have a biconditional conversation here because of all the theorems above. Two minor arcs are congruent if and only if their corresponding chords are congruent. So this minor arc AB is going to be congruent to this minor arc BC because we have our congruent chords. And without even needing to explain it, we also are then going to have the congruent angles. So the chords, arcs, angles, all related. Sound okay? Turn the page. In the same circle or in congruent circles. Again, we have this conversation about making sure that our circles are the same sides. My chords are congruent if they're equidistant from the center. And I'm drawing your attention to this distance here. And remember, distance is measured with a perpendicular line segment. Well, right now, stare at that picture and envision some triangles. Of course those chords are going to be the same length because each of these distances from the center are the same. My radii are the same. So if it's measured with a right angle, that sounds like more hypotenuse leg and CPCTC to me. Here's 3 circles. Revisit each of these and talk with your group about justifying each value of x on your mark it, set, go. I know that these 2 chords are equidistant from the center because the diagram tells me they both have a measure of 3. And I was hearing Aliska going, I'm not sure what any of the numbers are pertain to, and that can be tricky. And you always have the right to say, does this 3 represent the distance from the center of the circle? Yes, it does. So I know that if 2 chords are equidistant from the center of the circle, I know that they're the same. These readings tell me that this here, this segment that represents how far that chord is from the center of the circle, it happens to split that chord in half. So if this is 8, so is 8, which means this guy's 16. Do you see it now? All right, let's talk about the next one. I know that this distance here and this distance here, nobody told me what it's worth, but when I look at my 2 chords and I look at my congruence markings, they're both the same length. So if they're the same length, they're the same distance from the center, so x is equal to 5, because those chords are both 12. Are we okay with that? So these 2 conversations here are your biconditional relationship. If they're the same distance from the center, then they're congruent. If the chords are congruent, then they're the same distance from the center. Do you see how those examples give it to you both ways? Here they are, the same distance from the center. These 2 things are congruent. They both have a measure of 6.3, so I doubled it. These are my favorite. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. We're going to call these the big 3. And anytime you have 2 of these circumstances, you have the third. So taking 2 at a time gives you the third. If you have a diameter, so that's circumstance 1. and that diameter is perpendicular, that's circumstance 2, then you have a bisector. That's circumstance 3. If you look at this picture, I have a diameter. It's perpendicular. So I know that the distance from D to E is equal to the distance from E to F. Read the next sentence. If the diameter is a bisector, then it's perpendicular. If this is a diameter and it cuts this in half, then we have a perpendicular relationship. Here's our third scenario. If you have a chord that's perpendicular and it's a bisector, then you have a diameter. Your first consideration is the diameter. Your second consideration is it perpendicular? Your third consideration is a bisector. Anytime that you have 2 out of the 3, that means you're guaranteed the third. So pick any 2 of those 3. Diameter perpendicular, then it's a bisector. Perpendicular bisector, then it's a diameter. Bisector diameter, it's perpendicular. So whichever 2 you pick, you've got the third. Are you okay with that? So my favorite application of this is on the reverse of your warm-up that we will get to next time. So hold on to that warm-up because it's my favorite story that I want to tell. Your homework tonight is 2 practice pages, basically the rest of the packet. 3 practice pages, the rest of the packet. If you haven't done that Delta math, make sure you revisit it. I loved it when I heard somebody say, I'm going to have to go back and reread this. I want you to remember the curve of forgetting. When you go back and reread your notes, if you want to watch the video, it's all there for you to make sure that you learn it. The next time you walk into class, you should walk in with questions from whatever this packet you're still curious about. Make sense? Yes. All right. What?